Thumbs up, 1 second. All right, looking good. Cool, so today we're going to spend the whole lecture talking about programmability. So mostly this is sort of covering the software side of things. So what does the programmable interface look like from the point of view of the programmer? And I'm sort of presenting this earlier in the lecture, even before we've learned about how GPUs work, because people are doing projects and thinking about projects that are going to use programmable aspects, and because I'm hoping that in your assignment too, people will do a little bit of programmability, which is good. And also because the graphics hardware is becoming more and more programmable, and I want you to sort of understand what the fundamental thing is about that. Now, we'll be spending more time later on talking about what the hardware resources look like. I covered a little bit here. But this is a little bit more of the software area. And we're going to start with a little bit of history. OK, so the big transition that's going on now is that we're moving from, when we look at OpenGL, we can think of that sort of this fixed function kind of pipeline. Right? So OpenGL has, everything runs through this pipeline of stuff. And it goes through the geometry stage, and it goes through OpenGL lighting. And here's how OpenGL lighting works. Then it goes through clipping and culling and triangle assembly and projection and so on, all the way through. So it's this fixed pipeline of things. And what it was kind of configurable. So you can say, let's change the colors of the materials, or let's change where the light is, but you don't get to change the lighting model. You can configure it, but not really program it. So that's what things used to look like. And then the interfaces looked like features. Turn on a light. Put a light here. The light is this color. This material has this property, and so on. Okay, so all the, when you call GLX, you're generally enabling or setting particular features. Okay, so today we have, I wouldn't call it general programmability. It's moving from limited to more general programmability. But from the graphics point of view, it's not like running a general purpose processor, but at least you have the ability to do more programs that you wrote. You get to write a program to shade every vertex. You get to write a program to shade every fragment. And so this is sort of the era of having programmable shading, where instead of having this lighting model with these parameters and so on, you get to set some numbers. You get to pick your own lighting model, and you get to implement it in the way that you want to. The programming model is generally what we refer to as SPMD. So first, sort of what SIMD is. So if I write SIMD, what I mean on SIMD is single instruction, multiple data. So it's a hardware thing. And what it means is that I'm going to have a number of data paths and one controller. And that controller is going to control all these data paths. So I've got a bunch of data paths. Each one's going to be working on a different piece of data. And they're all going to be running in lockstep at the same time. Okay? So on the CPU, the equivalent is something like SSE or MMX. Right? There you have 4 wide. And when you do an add on one of them, you're doing an add on all 4 of them. Okay. The alternate to that is something called MIMD. Okay? And that has multiple pipelines also. But there, every data path has its own controller. Okay? So this guy can be running a different program from this guy, can be running a different program from this guy. Okay? So what's the advantage of MIMD for the programmer? Why might the programmer like MIMD? Pardon? Yes, but you can run stuff in parallel here. Right? You've got different data paths, and they're always going to be running things in parallel.
You can do different operations at the same time, though.
Okay.
On data, right?
Generalize that a little bit.
So each block will be, maybe one's an add, one's a subtract. They don't all have to be add, like in SIMD.
Okay. You have more flexibility because everybody can be running through a different thread of execution. Mm-hmm. Okay? And so this is clearly more flexible than this. This is a superset of this. Okay? What's the advantage of SIMD over MIMD? Okay. Simpler hardware. Okay? Right? Because you only build one controller instead of n controllers. So maybe that means that you can have more data paths for the same amount of area. So potentially this probably has a larger peak performance. Okay? But it's less flexible. does your program map to this particular model? So just as an example, I did my graduate work, we built a processor called Imagine. It was a stream processor, so it was a processor for doing multimedia kind of stuff, and it had a lot in common with what graphics processors look like today. In Imagine, the size of the data path was roughly the same size as the controller. Okay? So what that would mean is Imagine was a SIMD machine, and we had 8 arithmetic clusters in it, so a cluster was the same size as a controller. So we could either have 8 clusters and run in SIMD style, or 4 clusters and run in MIMD style. That's roughly the trade-off. Okay? So to move from here to here basically costs you half your peak performance. Now, if you look at a multi-core kind of processor, the multiple cores are definitely MIMD. Each core can be doing something completely different. So what the programmer really wants is something that gives you the performance of SIMD, but the flexibility of MIMD, which is, of course, impossible, but that's the goal. So what the GPU manufacturers are saying is that they okay, let's go back a second. So how do you actually program SIMD? Let's say you have tasks, and they're all doing something fairly similar. Okay, they're pretty much, they all want to shade a particular item, but they're not always going to run totally lockstep through the code. Okay? So if you do that, then you end up using these data paths in a way, you have to do a lot of manual management of that. You have to say, okay, we're going to write code that branches and then does something and comes here and so on. Okay? And like half the threads are going to go down this path and half the threads are going to go down this path. So in a SIMD, a traditional SIMD machine, what you have to do is you have to use masks to go down this path and then go down this path to make sure that each thread will only execute one of those paths. So what happens in practice is all threads have to execute both of those paths, okay? But one of them is going to be masked out by data. So your code kind of looks like this. You say, you calculate condition. And then, so then you say if the condition is, well, you don't even really get if statements is the problem. So then you do conditional writes. So you run the left path here, and then you run a lot of code. And at the end, you have a result here, and you only write it if the condition equals true. Okay? Then you have the right path here, and you have a bunch of code, and then you only write at the end if the condition equals false. Okay? So all code has to run down both paths, but you have to do all this manual management. Okay? So that's a pain, right? And it costs you performance. So you really want code here that's straight line all the time as much as you can.
So I mean, why can't you just have like branching? Because I know that in GPUs, branching is a huge, it costs you a lot of performance on GPUs. So
okay.
How come they don't have too much on, say, branch predictors or something?
So okay, but the issue is not so much prediction. Let's say he wants to run that way and he wants to run that way on the branch. Okay? So there's only one controller. There's only one program counter. Okay? So as this guy starts to run down this branch, it's not like he can stop and run down a different branch because there's only one program counter. Okay? All of them have to run down this branch. And then come back, and all of them have to run down that branch. Okay? Basically, you have code that's not going to branch at all if you want to run on a traditional SIMD machine. Okay? Not ideal. So a lot of the work is how can we find algorithms that map nicely to this SIMD kind of model? Okay. So what the graphics programmers do is they kind of do a compromise between these two models, and they call it SPIMD. So instead of, when I say single instruction, multiple data, I mean you have one instruction that's running at a time in this controller, okay? And everybody's running in lockstep on this, and you have to do all this manual sort of masking as the programmer. So what SPIMD says is, okay, we're going to broaden that a little bit. We're going to say that everybody has to run the same program, okay? But in the programmer's head, the programmer doesn't have to worry about this sort of thing, all the masking, all the straight lineification, all the conditional stuff is all taken care of by the hardware. It's still running in lockstep in practice, But you as the programmer don't have to manage any of that anymore. And it's pretty smart about being able to deal that for you. So you write code that looks like it has branches in it. And the hardware and the software will collaborate so that even though you think you've written code that looks like this, it will internally, using hardware and software, turn it into a big piece of straight line code for you. Okay? There's some more subtle things about that we're not going to really talk about today. But this is just a long-winded expression about what I mean by SPMD. So what the graphics programmers have decided is they will try to give programmers a model that's a little bit more flexible than SIMD. And they'll try to make it efficient in the hardware as much as they can. They still have this hardware model. It still has one controller and many data paths. And you still have to do this straight line code. But they're trying to make that as efficient as they can. OK, so any questions about what I mean by SPMD? Yeah.
So a good calculation for like how much overhead for branches would just be total both sides, or if it's nested, total every single type of branch that could be taken and add that together, and that's kind of the total runtime, or is that, are there some kind of ways they can get around certain things?
No, that's fair. So one of the questions is, do you total up every possible path, or do you total up every path that's actually taken? Okay, so let me sort of draw that. Let's say we have a piece of code that branches and then branches again. Okay? And then I wanted to take that code and I wanted to straight lineify it, right? So it's A, B, C, D. So then if I make this into one linear piece of code, then it goes like this, right? A, B, C, D. And the cost of running this code is the sum of all four of those. So the question is, let's say you actually only take B and C in your code. You never take A and D. If you've compiled your code to look like this, then it's still going to cost you 4 programs, even though you're only running 2 of them. So this is where the SPMD hardware helps you a little bit. Then it actually does take the branches, and so what would happen is you would come down here, and half the threads are going to take this branch here, and the other half are just going to sit there and not really do anything. Okay, and they're sort of waiting, and then all the branches that are, all the threads that are alive are going to take this branch here, and they're all going to run this, and nobody's going to run this piece of code at all. You don't have to worry about that as the programmer. The hardware takes care of that. It takes, so if you're not actually taking the branch, then it's not going to cost you anything. So then eventually it'll come back here, and the other half of the branches will run here. But then basically all you've run is B and C, and nobody's run A and D at all. Is that sensible? OK. Is that clear? Good question.
Well, I guess my question would then be, how could the hardware know? Like, how does it know beforehand if half of all the threads are going to run B, or if
it doesn't know at all. It compiles the code to look like this, pretty much. But it's smart in taking that controller and, it'll take this jump here and then come here, and then when we branch to B, it'll just skip over that and then run this. Then it'll go back here and decide, oh, I need to run to C. I'm going to come here, run here, and then skip out. Okay? So in that sense, it acts like a microprocessor would. It's actually jumping to the right piece of code. Okay. Now, it's still SPMD, not MEMD. It's not like it can be running 2 threads at the same time. Okay? If some branches are going this way and other branches are going this way, when this is being run, these guys are just sitting around doing nothing. Okay? I'll introduce one more piece of terminology, which is branch granularity. The question is, how many branches are running in lockstep at a time? Okay? How wide is this, is the question. Okay? Because if you had, you as the programmer would like that granularity to be as small as possible. Okay? Because then if you have, let's say you've got, all these bits here, like goes off to infinity, and these guys want to run A, and these guys want to run C, and these guys want to run D, and so on. Okay? Let's say your branch granularity is this big. Okay? All these threads need to run in lockstep. Thread, 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 thread. Okay? So a certain number of threads is the branch granularity. Okay? All these threads want to run in lockstep. Then half of them are going to be sitting idle at any time. Right? When these threads are running A, these guys are sitting around. When these guys are running C, these guys are sitting around. Okay? Now, if your branch granularity is this wide, okay, half this wide, then you don't suffer any penalty at all. Because you run these guys, they all run A. You go to the next unit, these guys are running, they'll all run C. These guys will all run D, and so on. So your goal as the programmer, or your desire as the programmer, is to make the branch granularity as small as possible. Okay, what's sort of the unit of SIMD-ness? What's the unit that absolutely has to run in lockstep all the time? How big is that? So a nice thing about graphics hardware is that used to be very large. That used to be a number that was like thousands, 1,000 or thousands of threads, thousands of fragments that would all run in lockstep at the same time. Okay, so if any of them took a branch, all of them would have to take the branch. Today that number is much smaller. That number is roughly 16. Okay, 16, 32, depends on the hardware. It is a smaller branch, and it means that branches cost less. Because now if one person takes a branch, only 15 other guys are going to take the branch, as opposed to thousands of other guys who are going to take the branch. Okay, so that's our programming model. Yeah, we've just spent 15 minutes on that. Cool. Okay, we've also moved from having, how do we program these things? We have an assembly language interface, was sort of the original thing, and now we're moving toward actually getting to write our shading code in a higher level language and moving toward whole programming systems that are built around that. So that's good for the programmer too. It used to be you had to write all your programmable code in assembly language. Today you have some nice languages that help you do that. Okay, eventually we want to move to something that's more general programmability, where we don't just get to write a program that works for that works as at one stage on vertices or fragments. We want to get to write the pipeline the way we want. Okay, we want to sequence the pipeline with this stage first, and then this stage, and then this stage. Can't do that yet, and there's no tools to let us do that yet. But people are very interested in being able to do that because people want to do newer, cooler kinds of effects. So that's where we're going, and in 5 years, hopefully we'll get to talk about that a lot more. Okay, so we're going back to 1984. So SIGGRAPH is the large graphics conference in the graphics community, sort of where it's the most prestigious graphics conference. So Pixar came out of Lucasfilm. So the first thing that Pixar did was, Star Trek II, I think, Wrath of Khan. Khan died yesterday. Did you see that? It's very sad. So there's this scene with this Genesis project. Right? And they have like this computer simulation of what happens when they drop like this Genesis bomb on the planet, and then like the planet totally blooms, and it's really cool. And so they have this really sophisticated like path that the spaceship is taking, and eventually it gets to this mountain range. And you should watch this yourself sometime. And this mountain range is like growing up, and the ship is flying through, and then like it almost hits and then goes straight through. And so this was sort of the first computer animated sequence that was done as part of a movie. It was really very cool. And George Lucas loved having really complicated the flight path, like really complicated camera paths, and they were able to do this on a computer. If you actually watch it very closely, they developed the mountain range as a fractal, so it wasn't quite predictable where it was going to go. So fractals are a little bit random by their very nature. And so this mountain range is growing up, and they didn't really have time to like simulate it, render the whole thing, find out that there was a collision, and then start over. Like they had this really hard deadline, they couldn't make it. So if you actually watch it, the problem was that they've built this whole thing up, and it's coming up, and they find out at the last minute that it actually is going to collide. And so if you actually watch the movie, and you go frame to frame, you'll see like the mountain range come up, and it's about to go, and then suddenly this whole triangle like disappears. There's this little notch that appears in the last frame and goes straight through. Okay, so then it was at Lucasfilm for a while. It spun off into its own company called Pixar. And then these guys started doing just amazing stuff. And so in 1984, this was just the most amazing set of papers. And all these have had continuous and long-lasting impact. And these were all done by people at Pixar just in that year. So Albie Ray Smith was one of the founders. He's the one who actually named Pixar. He wrote up a lot of this fractal and plant stuff that had been done. This was some of the first SIMD work on actually building graphics hardware. This is like the fundamental ray tracing paper. We'll talk about this later in the class. This is a particular way to do compositing that's part of Rays, which is the basis for RenderMan. This is what we'll talk about today, shade trees. So this was sort of the first idea about programmable shading. And then we'll talk about compositing later on. And this is the fundamental compositing way that we composite things today, the algebra for doing composition. So it was a really good year. Okay, so here was sort of the movie they were doing in 1984. And this movie just blew people away when they did it. It was called Road to Point Reyes, and so had for 1984 just incredible visual effects. And these were some of the shots from the film. And so what they really had here was some interesting ways to to do programmable shading. Okay, that was their goal. What we're sort of showing here is how we composite different things together. Okay, and this is sort of the algebra for being able to do that. But each one of these objects had its own program that computed its shading. And the way they defined this, so Rob Cook did this in terms of what he called a shade tree. Okay, so the top of the tree is the result that you want. Then you have this big expression that you put together. And so we've learned a little bit about shading, sort of what's the OpenGL shading model. The OpenGL shading model is called the Phong shading model, and there's 5 terms that go into the Phong shading model: the normal vector, the light vector, the normal vector again, the half vector, don't worry about that yet, and then the specularity. And so if you think about casting what that looks like in terms of a tree, this is the way you do it. You combine this and this, and you do some sort of operation to compute the diffuse color. You take these 3, you do some sort of operation to do the specular color, you add things up, and it gives you the final color. Okay, this is what OpenGL does. Okay, and so what he said is, we really want to generalize this. Okay, we like this tree structure, but instead of giving you a fixed tree where all you get to do is fill in the endpoints, you should get to build your own tree. So if we look at, this is straight out of the paper here, he said, okay, we want to make something that looks like copper. Okay, what's that going to take? Okay, well, here are the inputs to copper. So there's some weights here, there's an ambient color, the surface roughness of the copper. Okay, and then you get to define your own tree. Okay, you get to build this tree in any way you want. Okay, this probably doesn't seem super sophisticated. Like, okay, big deal, it's a tree. We've done expression trees before, but it's the first time it had really been applied to graphics. And so he sort of defined the way that this worked. So you could define this. You could do any sort of arbitrary tree that you wanted. Here's another one. This is the color, I guess, the normal for grass. Okay, so there's if we go back and we look at the pictures here, there's some grass in these pictures. I'm just looking at the names here, and I actually don't see any grass. Anyway, trust me, there's some grass there. And so here's how you compute the normal vector for grass, and then you take that result and you put it into the shade tree for grass, just for the grass color. Okay, so he defined sort of an algebra to be able to do these things. And so he defined a bunch of operations. Okay, what are the things you can do in the tree? So basic arithmetic stuff, dot products, normals, and so on. And then showed how you can organize these things into trees. One of the other things that he did was really kind of cool is he separated out the trees for defining lights, for defining the way that light interacts with surface, and defining the atmosphere that is between the light and the surface. So if I decide to light a cigar in here, there's all this cigarette smoke in here. That's something that you would want to model in your system and have sort of an atmospheric shader. Okay? Fog would be part of that. Okay? That would be the sort of thing you'd want to model. And so his system had these things separated, which was cool. And then he had different kinds of trees too. Okay, so shade trees dealt with surface reflectance kinds of things. Light trees define lights. Atmosphere trees define these atmospheric effects. Displacement maps are how you take a surface that's flat and then make it a little bit bumpy. Okay, so if I had like an orange, for instance, maybe I'm going to model an orange as a sphere, but it's going to have another function associated with it. It's going to put all the bumps on the orange. Okay, so that was all really cool. And then he had a language. Okay, very simple language to put these trees together. Okay? And this probably doesn't seem like rocket science, and it's not rocket science, but it was big ideas at the time, and it really allowed people to have much more complicated shading effects than they had before. And these were some really good ideas, and particularly factoring things out ended up having long-lasting effects. So this is actually exactly how RenderMan works today. RenderMan does this sort of factoring. Okay, sort of the next thing was the next year. Ken Perlin is, he's at NYU now. He's a faculty member there. Amazing guy. And so he extended Rob Cook's shading stuff. And so what he really added to the table here was this idea of, okay, well, a tree is pretty straightforward. We'd like to be able to have more complicated things than just a fixed tree. We'd like to be able to have conditionals and loops and do SIMD kinds of things and functions and so on. Okay? And that wasn't really in Rob Cook's language. So he took the ideas that Cook had and he added this language to it. And so this was great. I've got some visual effects next. Probably the thing that he did that this paper is most cited for is introducing this idea of noise. And so here's some of the images that he had, which were, again, pretty awesome for 1985. Pretty awesome today, too. I mean, these are really nice looking stuff. So this idea of noise was Well, if you look at computer-generated pictures, they're really, they look great, right? Everything looks crisp and clear and shiny and new, and real things don't look like that. And so what we actually want is to put a little bit of randomness into the image, right? That wall over there isn't, completely flat. It's actually a little bit bumpy, and there's some cracks in it and so on. And a lot of times the way you know if something's computer-generated or not is the computer-generated ones look too good. They look perfect. Everything looks great. Nobody has acne. Everybody has perfect skin. So how do we put randomness into the process? And so the thing that Cook introduced was this idea of noise. And it's a function that noise is a function, and it has particular properties such that it's very useful for generating, you can use it in many ways to generate things that are noisy and have a little bit of randomness in the process. So how do you do this sort of contour here? Okay, that's something you do with noise. You can generate this marble pattern with noise. So it's not a completely random function. It has characteristics that you can use for these sort of effects. But it makes things look much more realistic. Like, that's something I could legitimately think of as a photograph during an eclipse, for instance. This is not perfect waves here. There's some uncertainty attached to them. So, and if you look at really high-end rendering systems like a RenderMan, noise is a fundamental piece of them. All sorts of RenderMan shaders are going to have noise all over them. And it makes it look more realistic. Okay, so Rob Cook sort of said, okay, here's shade trees, and here's how we're going to separate them out. And Ken Perlin really thought about the language part of this, and together what that really generated, what allowed to happen was in 1989, and this was this idea of the definition of RenderMan. So RenderMan is the shading language that's used at Pixar. It's used for most high-end graphics, period. Like most film studios will have RenderMan licenses and will do all their high-end graphics in RenderMan. So it's the best thing out there. Pat Hanrahan's the lead guy. He was my co-advisor at Stanford, and he was at Pixar at the time. He talked about, so he gave a lecture on sort of the history of RenderMan, and he brought in the original RenderMan draft with him. And he said, I just wanted to show this to you guys. Like, it has all these comments in it, and he opens it up, and there's all this red ink in it, and people have given him comments. And his boss had taken, the RenderMan specification and circled RenderMan in really big letters and wrote, "Stupid name." Okay, but it was like 1989, and it was when the Walkman was really big, and that predates a lot of you, but it was a really cool player at the time, so they thought it was a good name. So Pat never agreed or never thought that like this sort of beta name that he made up would end up actually making it into a product. So the next project he did, he named it Pimple to make sure that it would never make it into another product. Okay, so this is one of my favorite papers in all of computer graphics. Every time I read this paper, I get something new out of it. It's really a fantastic piece of work. So it really it took the sort of ideas that Cook and Perlin had and put it together in a really, really nice system. So I think the thing that really blows me away about this is that he developed an interface to this that would work with numerous rendering systems underneath. And you read it, and that's the thing, like the second or third time I wrote it blew me away. So we're learning about sort of a polygon pipeline here. How do you take a polygon pipeline and make, put in triangles and how they work? We also talked about a ray tracing pipeline, right? So you can build a ray tracer and actually model how light goes around the scene and how it interacts with things and also get very nice pictures. And if you look at the specification for RenderMan, you can take RenderMan and build either kind of pipeline underneath, okay? Which seems amazing. And so it's really cool to read about the sort of interface that he chose that allowed it to do that. And in fact, you can do that today with RenderMan. Pixar makes a RenderMan that's basically based on a polygon pipeline, kind of like the one we've talked about. But people have built RenderMan implementations that are all ray traced implementations. Okay, and they use the same interface, which is totally amazing. So there's a lot of great ideas in here, and it's a really nice piece of work. So this is kind of the thing everybody would like to shoot for. Okay? We'd love to be able to run RenderMan kind of shaders in real time. Okay? That's too hard. So, and it's too hard because, we want to render millions of pixels a second for hundreds of frames a second. Right? So we're rendering probably close to 1 billion pixels. Okay? How many operations can we realistically do on each pixel? Today, maybe 100. And we're talking about RenderMan shaders that will do hundreds of thousands of operations on every pixel. So there's this long way to run here. If you're doing something like noise, noise is hundreds or thousands of operations on every pixel, okay, to actually get the noise calculation all done right. So this is sort of where we'd like to be able to go, and how do we get there? And so the nice part has been we started out with having very simple models as far as what the hardware can do, and it's only running just a few things on every pixel. And as time has gone on, those have got more capable. Today we're up to the point where we can run dozens or hundreds of operations on every pixel going through. And I'm going to talk about what those interfaces look like. Okay, so any questions about sort of the history here? Okay. So let me introduce just a little bit about what the hardware looks like so you can keep this in mind as we're doing more discussion here. Okay? So I'm sort of showing you historically what the hardware looks like and how that's changing today. And I want you to keep those two mental models of historical hardware and today's hardware in your head as we talk about the rest of this. Okay, so here's our graphics pipeline. We've got all these pieces to the graphics pipeline. Now, let's say we're running this on a CPU. All right? So we sort of walk through these stages, and if we're doing it, we have a primitive, or maybe a group of primitives, and we all run the command stage on those primitives until we're done with those primitives. Then we take the result, and we use the same set of primitives, and we run geometry on it. And then we run rasterization on it, and so on. So what we're kind of doing is we're taking the pipeline here, and we're cutting it up in time. All right? We spend a certain slice of time on each different piece of the pipeline. And at each step, the entire machine is working on that one piece of input. Okay? Then we switch to a different stage, and the whole machine is going to work on that. All right? But you understand what I'm saying when I say we take the pipeline and divide it up into time. Okay. Traditional graphics hardware takes a different approach. Traditional graphics hardware divides the pipeline up in space. So it takes this big chip, divides it into all these pieces, and then each piece gets a different piece of the silicon and works on a different piece of the pipeline. Okay? So this section of silicon is only going to do geometry processing. And this section is only going to do rasterization and so on. Okay? So it's a very different approach. Okay? What's the advantage of this approach? Okay, what would seem good about doing it this way? Because it's very different than a CPU does it. Okay, you can pipeline it. So, and that gives you the advantage that you can have many things in the pipeline at once, perhaps. But it also gives you the advantage that the whole machine is going to be busy at the same time. But on the other hand, in the time-sliced approach, presumably the whole machine is going to be busy just doing one stage at a time. So is that really a win? Okay, it depends on how you implement it. Okay, that's not the big win necessarily.
You can optimize each step of the pipeline to do its job the best it can do. Okay.
So this is the big win. The big win is the win of specialization. That if I want to build a rasterizer to only do rasterization, I can build silicon that's going to be optimized just for that task. And it turns out you can get big wins from being able to do that. You can do rasterization an order of magnitude faster, better, less power, less area than you can if you use a general purpose machine. Okay? So that's really the win, that no matter how you built the CPU, it just couldn't keep up. It couldn't do everything it needed to do fast enough. But if we specialize to particular tasks, okay, we can get more efficiency. Now, what's the bad thing?
If you have lots of triangles and not much to draw, then it's going to bottleneck in the geometry pipeline, and the rasterization won't have anything to do, etc.
So let's take a look at the time slice pipeline. Okay? Let's say we send in a bunch of giant triangles. Okay? What that's going to mean is we don't have a lot of geometry work to do. So if we look at time going down this axis, we're going to spend this little tiny amount of work doing geometry and this giant amount of work doing fragments, right? Then what we do is we send in a whole bunch of little tiny triangles. Okay? And then we have this giant amount of geometry work and this little tiny amount of fragment work. And that's okay. That's great because we divided the pipeline up into time. The machine is busy all the time, and it can easily change what it's going to do. Okay? Let's say we're over in this model. Okay? Well, you're basically going to be limited by your slowest stage. Okay? If you have all this geometry work to do, then your fragment pipeline's sitting there just twiddling its thumbs, nothing to do. If you're limited by your fragment pipeline, your geometry work's just sitting there twiddling its thumbs, nothing to do. So there's a potentially large load balance problem when you design things in this way. Okay, so this is really this is really the trade-off that we have here in building these things. So this way, you've got some problems with specialization. Okay, this way you've got some problems with load balance. Historically, this has been the way that we've done it. And as the pipeline has become more programmable, the load balance problems have become more significant. And we're moving back toward doing it more like a CPU. Okay? I don't want you to think this is this discrete spectrum with only 2 points on it. It's a big spectrum from what I call a task parallel approach versus a time multiplexed approach. Okay? So it is moving back toward being more time multiplexed. And we'll sort of see some pictures why. So this is sort of the oldest GPU I could actually find. Okay, I guess this was made by ATI. Some of you might have had these when you were younger. If we look at this, it's not really a diphode or anything, but you've got lots of pieces on it. All these pieces are fixed function. Okay, there's nothing programmable on this chip at all. And you got a bunch of units that are sort of scattered all over the chip. Okay, this is very much a task parallel kind of approach in terms of the way we built this GPU. Okay? Nothing programmable, though. As we move forward, we start to see the programmability becomes more important. Okay? So we still see this as a pipeline kind of approach here. Okay? It goes from top to bottom, just like our picture. Okay? But now we have units that start to be programmable. So those vertex units, these fragment units, these are programmable units. Okay? They're still programmable stages in a pretty fixed function pipeline. Okay? But we're starting to do some programmability here. And what we're going to do for the rest of the lecture is sort of look at what's in those boxes and what it can do. All right? And then if we look today, it's much more of a programmable. So this sort of has programmable stages in a fixed function pipeline. Okay? This is built around the programmable parts, and it has a few fixed function parts around a programmable core. Okay? So here the pipeline is sort of king. A fixed function pipeline is king, and we've done a little twiddling with one of the units. Here, the most important thing is the programmable part, and all the fixed function parts are just little units on top of it. And that sort of speaks to how important programmability is coming. If we look at the amount of work that goes into a scene, it used to be like 1% programmable, and most of the flops went to fixed function things. And as time has gone on, the programmability becomes much, much more important. Okay, and now it's mostly programmable stuff. If you look at a Pixar kind of scene, it's 99.99 whatever. It's just a question of how many nines percent programmable. And most of the work is going to the programmability, and that's the direction that we're going. Okay? And because that's the case, it's really hard for it to do load balancing between the programmable stages, and it makes a lot more sense just to have one big pool of things that can do any programmable stage. Okay, so what we're going to talk about for the rest of the lecture is, in particular, these two stages. This vertex stage, what happens there, and this fragment stage, what happens here. Okay, so what is the program? What do the APIs look like to the programmer? What sort of things can we do there? And again, I'm going to sort of do this historically. I'm going to start with something simple and then move more toward what we have today. Okay, so where do vertex programs fall in the graphics pipeline? Okay, so it's sort of this geometry part here. There's a bunch of stuff that's happening here. Okay, in particular, what we've talked about in at least a little bit of detail is the transformation, the lighting, and those are kind of the only two that we've really talked about. You can generate texture coordinates, you can do clipping, and so on. What we're interested in is this part here. Okay, these are the things that we're going to do instead of with the fixed pipeline. We're going to do them with a vertex program that we write. It will replace those stages of the pipeline. We're going to write something that will do the transformations, that will calculate a color at every vertex, and if necessary, generate texture coordinates. Okay? So that's the part of the pipeline that we're replacing. Now, as we do this discussion, the hardest part to get used to, okay, is the most important thing I'm going to tell you all day. When you write one of these programs, the way you have to think about it is that you write one program, but it's going to run on every vertex. Okay? Your program doesn't look like a loop over all vertices. Your program is the inside of the loop. You write one program, but it runs on everything. Okay? And that's when we think about that approach, that's what we mean by this programming model. Okay, the programming model is such that you write one program and it's going to run on everything. You can think about different ways to do it, but that is the programming approach that the graphics hardware is giving you today. Okay, it's this SPMD model. You're writing one program that's going to run over all these pieces of data. Okay. Now, one of the goals here is that we want to make this thing run fast on hardware. And what we didn't want was for to take this fixed function stuff and change it into something programmable, and then it's going to run 5 times as slow. Okay, so originally I said, you know what? What we're going to have to do is we're going to have to make sure that Vertex program is just as fast as what it replaced. And to make that happen, we're going to have to restrict what we allow the programmer to do. So how do we do that? Okay, one thing you do is you make sure that there's no dependencies between elements. Okay, you can't say my vertex program is going to depend on the vertex that came before me. Okay, every vertex is independent. Okay, there's no expansions or reductions. Okay, one thing comes in, one thing goes out. Period. It's not like you send in one vertex and you get 3 vertices out. Doesn't work. You can't send in one vertex and get 0 vertices out. Definitely not. It is 1-to-1. One thing comes in, one thing goes out. That makes it easy to parallelize. Okay, it makes it easy to parallelize because you have one processor, great, 1 in, 1 out. You have 2 processors, great, 2 in, 2 out. Okay, there's not any ordering. There's no issue with dependencies between them. Every pipeline is completely separate, and that's good. That's good from a hardware point of view. Okay, so what sort of things can't we do with a Vertex program? Okay, we can't do like tessellation kinds of things where we send in one triangle and get out a bunch of triangles. Can't do that. Can't do primitive assembly where we send in a triangle mesh of vertices and we get out a bunch of triangles. Okay, that also implies that there are dependencies between the vertices. That's right out. Can't do clipping. Okay, because clipping means you send in one triangle, you might get out 0, you might get out 6. Okay, so these are things that we happen with more special purpose hardware. All we're interested in doing is the 1 in, 1 out model. Okay, so the way they do this is a program they call a vertex shader. Okay, and this is sort of a block diagram of what that looks like. Sort of the core here is a vertex program. The first version of vertex shaders would allow you to run up to 128 instructions. All right, so you've got a bunch of inputs and a bunch of outputs. This is sort of the data path, and then you've got some registers there and some read-only registers here. So this looks like very simple hardware, and it is. Okay, but this is the hardware that they would be able to give you. Now, here's Microsoft's really cool picture of it, but it looks pretty similar. We have this ALU in the middle that does all the math. You have a bunch of registers and a bunch of constant registers. You have inputs and outputs. Okay, and this is sort of a picture of what happens in the processing of one vertex. Okay, so we're going to go through sort of these pieces here. What is the input information per vertex? So what is the input information per vertex? What do we expect as the input to this pipeline?
Location and normal, maybe?
Okay, position, normal. That's 2 things. That's great. All right, what else?
Texture coordinates.
Texture coordinates. Okay, what else?
Color.
Color, fantastic. You pretty much nailed most of them. So we note along the top we have up to 16 vectors. Okay, here's what the vectors actually look like. Position. You can have weights if you want to do some blending kinds of things. Don't worry about that. Normal. You can actually send in more than one color. You see that I've got a little bit of formatting problem right here. Fog coordinate, we didn't talk about that. And then a bunch of texture coordinates. Okay, so one interesting thing to look here is, we've got this mapping here. We're not sending in one thing per element here, per register. We're actually sending in 4 things. Okay, this is 4-wide processing. So we're not sending in a 32-bit floating point in each one of these registers. We're sending in 4 32-bit floating points. So we're actually sending in 128 bits wide. Okay, why is this 4-wide thing interesting for graphics?
XYZW and RGBA.
Okay, we do lots of operations on 4 things in parallel. Okay, if we're doing a color calculation, we're doing these light calculations, we're going to calculate red, green, and blue in parallel, and also the transparency coordinate alpha. We talked about how all our transformations are done on 4-wide arithmetic because we have 4x4 matrices. Okay, so that's what we have here, that we're sending in 4 things at once. So this immediately makes it a little bit different than what you see in a microprocessor. A microprocessor usually has something that's 32 bits wide. That's how wide its data path is. This processor is 128 bits wide, and it does partitioned 32. It does 32 times 4 vectors. Okay, a vector that's 4 wide.
I have a question. So how do they specify the? I mean, for example, if you want to geo color F or just geo color D or something like, you want to
If you want a scalar color.
Yeah, scalar color.
Okay.
How,
So let's say we'll look at the fog coordinate here, right? Fog coordinate is there's only one thing we care about, right? And it's basically distance away from the camera or something. What do we do? And the answer is you throw away the other 3. Okay, and that's the decision they made. And they said, basically the kind of things that we're going to run on this are mostly 4 wide. Sometimes we'll have some 1 wide stuff, but mostly they're 4 wide. And we're going to optimize for that in our hardware.
what if we use double instead of float, like color or just normal? Or...
Okay, you don't. So here's something else about the Vertex processors. All they did, at least to this point, was floating point. They did 32-bit floating point, period. Okay? If we go back a little bit, if you actually did happen to send in a double, okay, then the command processor will take care of that and change it to a float for you. Okay? So this is it's a 4 times 32-bit wide processor. Okay. So what comes out? Okay. Well, what needs to come out is the position, and you as the programmer are responsible for doing that transformation. Okay? You have replaced the transformation matrices in there. Okay? Also, color needs to come out. You're now computing lighting coordinates possibly per vertex. Sorry, lighting calculations per vertex. So you're going to send out a color. Evidently, you can send out 2 colors that face forward and 2 colors that face backwards if you want to calculate all those. Typically, you're going to spit out 1 color. All right? You'll send out transformed texture coordinates and some other weird stuff possibly, but these are the outputs.
So if let's say you program your vertex shader the same way as a fixed functionality, will you get about the same speed?
So if you're, NVIDIA or AMD or S3, do you want that answer to be yes?
Yes.
Yes, you do. And so it was very much a design goal when they started doing this that they would be able to do that. Okay. So you can think about doing that in more than one way. One way is, okay, here's what we're going to do. We're going to have a programmable unit here, and then we're going to have another fixed function unit here. We're just going to put both of those things in, and we'll run the fixed function stuff down this path, or we'll run the programmable stuff down this path. Cool. Or you could say, all right, we're going all in. We're only going to build the programmable stuff, but we're going to make sure that the programmable stuff is good enough that it would match the performance as if we built it in fixed function. Okay? I don't know what they did. Either one of those would make sense. Okay? But eventually, you want to get to the point where it will have only the programmable stuff, and it's still going to be able to run fixed function.
I'm a little confused about the last slide.
Okay?
So you said the input to the ALU was 128 bits.
Right.
But there's 16 times 128. So are each of these going into your ALU to be calculated on?
Okay, so this picture is sort of showing those 16 things map to 16 input registers. So you'll write a program that can address each of those 16 input registers. And you might not use all of them, but you can say, all right, now I need to compute the position. I'm going to need to get the position out of vector 0, and then use some temporary registers and so on to make that calculation.
So each calculation of the vertex might take more than one call cycle, because you might have to go and grab, say, vector 0 and then vector 1 and then vector 2.
Well, but these are close. They should be. It's not like you go to memory to do them. By the time they reach here, they're in essentially a little tiny register file that's only an input register file. So it should be something you can fetch and compute on in one cycle. But yes, it's possible. It's just like a microprocessor. You could have things that would take.
Use all 16 of those things on one clock cycle to do some calculation.
Well, you could probably fetch one of them and do something, or fetch 2 of them and do something. Okay. And that would really depend on the instruction set. So what the instruction set looks like is just like I think I have coming up here. I'll go to hardware in a second. Here's the things it could actually do. Okay, so this is the instruction set. So these are ones where, and you'd have to look at the specifics, but to move, to take one temporary register and move it to another, or to take an input register and move it to a temporary register or something. Okay? It could do, all right, let me go back a slide and talk about hardware, and then I'll come here, because that's a better order to do it. This is the only time anybody's ever written anything up about it. They went to SIGGRAPH. This was in 2001. And they said, what's our hardware actually look like? Okay? So it looks a lot like the picture we just saw. It's got a bunch of what they call here IB as input buffers. So this is where these inputs come in. It's a little register file for those. Okay? It's got a bunch of output buffers here. Okay? Registers, these are temporary registers. Constant memory has constant registers. What sort of things might you put here? Okay, what's a constant thing you're not going to touch? You're not going to change in the calculation.
Your matrices, your transformation matrices.
Transformation matrices. What else?
Vector.
View vector. Sorry?
The light position.
Okay, light parameters. That would be good. Hey. So light color, light position, light normal. Okay? Material properties. Okay, these are things that are not going to change from vector to vector. Sorry, from input to input. So that's good. Okay, so that's all sort of the storage all the way around here. This was kind of interesting. So they said, well, a lot of these operations end up being vector-only operations. Okay, we're going to build a semi-vector unit. It's 4 wide. Okay, so it's going to do 128 bits at once. It's going to do 4 adds at the same time, or 4 multiplies, or whatever else happens to be in there. And most of the instructions run in here. Then they had some stuff where they said, all right, there's some things where we're going to use the special function unit, and we're going to put special functions in here that we don't want to build 4 of them, and we don't think you want 4 of them. Instead, if you want to run 4 of them, you're going to have to run it through 4 times. It's only going to operate on one thing at once. Okay? We don't want to build a reciprocal unit. Okay? They didn't have a divide, but they do have a reciprocal. So if you want to do a divide, you do reciprocal and then multiply. Okay? So these are the instructions they have. Reciprocal square root. Turns out to be very useful in like lighting things, normalizing vectors. Reciprocal square root is great. Logarithm and exponent, and I'll talk about this one in a second. All right, but these are things where they're in the special function unit, and it only runs on 32 bits at once. Okay, so that was sort of their hardware trade-off. They said the common things we're probably going to put over here, and we're going to do them all 4 wide. The uncommon things we're not going to spend as much money. We'll just do them 1 wide. Okay, so what is the instruction set? Oh, other things. Okay. So then we have these little guys here called SWNEG, and that stands for swizzle negate. Okay? And so you have 4 things that are coming in at a time. So swizzle lets you take those 4 things and put them in any order you want. Okay? You can bring them in as X, Y, Z, W. You can bring them in as W, Z, Y, X. You can bring them in as X, X, Y, Z. You can put them in any order you want. That's what swizzle does. Negate will take any of those 4 and put a negative sign in front of it. Okay? So the consequence is you will see an addition here, but you won't see a subtraction. You won't see a subtraction because all you do if you want to subtract is you flip the negate bit on all the inputs, all the second inputs, and then you add. Okay, so they got to have fewer instructions as a result. Okay, so move, just copy from register to register, multiply, add, all in one. Reciprocal square root, exponent, log. Min and max takes a vector. You know, what's the biggest part of these 2 vectors? Okay. SLT, set if less than, set if greater than or equal. ARL, which is a addressing instruction. Dot product, so we'll take 3 or 4 wide, 2 vectors, and then compute the dot product of those. Okay. Turns out to be very useful in graphics. You'd never see that in a CPU instruction set. DST takes 2 vectors and figures out how far away they are from each other, like 2 points. Right. It calculates the Pythagorean distance. Okay, and LIT, and this comes back to Stanley's question about, we want this to run nicely compared to fixed function units. So LIT turns out to implement the entire blend lighting model that's part of OpenGL. Okay, so when we saw that shade tree earlier that had like 5 components in it, and it does like a diffuse component, a specular component, and puts together in a particular way, and does all these dot products, all that is in this one LIT instruction. So it is the most special purpose instruction you've ever heard of. You hear about like CISC and RISC kind of processors and CISC and things that are kind of special purpose. This is like CISC to the nth power. It's crazy CISC. Okay, it only does this graphics thing, and it's specifically because they needed this thing to run just as fast as doing it in fixed function.
At what granularity would you change your, say, your Vertex program, like per frame or?
So that's a good question. So so you might think it's kind of expensive to do that, right? Because there's a lot of state associated with that. I mean, you probably have to change all your constant vectors. You have to load in, new Vertex program. You only have a few instructions in there. So you might think it's kind of expensive. And so in practice, I understand that people, even today, people have like a big program that's going to shade everything in your scene. And it's just going to have this giant switch statement at the top and say, either you're shading that, or you're shading that, or you're shading that, like different things, rather than having 3 separate programs. So it's common. So you want a Vertex program to apply to many, 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 many vertices, as opposed to just applying to just a few, because evidently switching those is still expensive.
But every frame you would change the program, right?
Well, you might or might not. I mean, you might have the same vertex shader that's going to go for the whole program. The goal is you don't want to change it a lot per frame. Okay? You don't want to change it every 5 vertices. That would be bad. I don't have exact numbers for you, although you can ask Eric if you're really curious about that. Okay, so So notice there's no branching instructions or conditionals. Okay, you can do sort of max and min, and that's a little bit of control things. This set if less than can let you use some masks, but basically you're running straight line code, right? You didn't see any branches, you didn't see any if statements or anything like that. So just to show you the sorts of things that it can do, all right? So here is a vector cross product. Okay, you have a 3 vector and another 3 vector, and you want to take cross product. Okay, turns out you can do that in 2 instructions. Okay, remember the way you take a cross product is you sort of do 3 multiplies this way, and then you subtract off 3 multiplies that way. Okay, but remember we have 4 wide arithmetic. So this multiply here is doing a multiply in that direction, and notice it's doing a swizzle because it's got to sort of shift one of those all the way around. And then multiply add adds the result to this with a negative there, so it's actually doing a subtract, but the multiply is going the other way. Right? So it's 2 instructions for a cross product, which is pretty awesome. Okay? Vector normalize, that takes 3. So we have a vector, and we want to make sure it's a unit vector. All right? So you take the magnitude of the vector, reciprocal square root, and then you multiply it through. Okay? And that'll make sure all those are normalized. So these are things you're going to do in graphics fairly often, so you're going to make sure they're kind of fast. If we wanted to do the graphics pipeline, okay, just the fixed function graphics pipeline, this is what it looks like. Okay, so what are we actually doing here? All right, 4 instructions for transforming position. Okay, this is a dot product, right? So if we're doing a 4x4 matrix multiply times a 4x1 vector, it's going to take 4 dot products. We need to transform the normal, which is 3x3, so 3 dot products. Okay, this is calculating the starting part of the lighting model, and then lit. Okay, this magic instruction that does all the blend lighting model. Bam. Takes these 3 things and then does everything else in it. And then you add them together using these instructions here. Okay, so lit does a lot in there, although clearly it doesn't do everything. So this is 13, 14 instructions. So you better make sure that's at least as fast as doing it in fixed function hardware. Yeah?
Is it kind of like some CPU architectures where it's like register-specific certain commands? Like you'll always use this register to store the information from computing these things?
Right. So in CPU architectures, usually that is a convention. Like you have a convention, you're going to put the frame pointer or the stack pointer in this particular thing. I mean, I think that's what we mean when we make this list, right? This is a convention. I think you could probably get away without doing it, right? To say register this and you can do your own thing, but you should use it in this way. That's my understanding. Okay? And notice this has like, register names that are built in. You don't have to know the numbers. Okay? And so I think people in practice do that. Okay. So as the shader model gets more sophisticated, we get more features, right? More registers, larger programs, more, which is good. Shader model 3 put texturing into the Vertex pipeline for the first time. You could, let's see, not just swizzle and negate, but you got an absolute and a saturate modifier, which is good. You can have sine and cosine, and you don't have to define your own constants for those. It's starting to have branching in it too. Okay, and the hardware takes care of all the branching characteristics and so on. Okay, so here's sort of what it looks like in this pipeline. Okay, so this is what they actually built a few years later. Okay, and this doesn't look too much different than the other one. Remember, we had sort of a scalar unit and a vector unit in the big black picture that I showed. Okay, and now we've got a separate branch unit here and a separate texture unit. Okay, this is what sort of the hardware looks like underneath. They don't release a lot of information on what's actually happening inside, so it's the best I can do. Okay, any questions about the Vertex pipeline?
What is its MIMD?
So this is a marketing slide from Nick. Okay, so this is actually, okay, so this is interesting. So one of the questions they had was, should we build something SIMD or should we build it MIMD? Okay, and what they found is, so how do you decide that? Well, if you have code that needs to branch all the time, okay, it really does, then building something MIMD makes sense, right? Otherwise, you really lose some efficiency. If it turns out your code doesn't branch much, then it doesn't make sense. And so what NVIDIA did, at least in here, they said, you know what? Our Vertex code ends up branching a lot. So we're going to have a separate program counter for every unit. Okay? And they actually, at least in the 6800, it was a MIMD architecture at the Vertex level, and it was a SIMD architecture at the vector level, at the fragment level. So that is a decision they made. Today it's back to being more SPIMD and less at MIMD. Okay? But they make this evaluation at every time.
As far as not doing graphic processing, but normal kind of processing, so this looks very similar to like a normal CPU. So is it like now that there's branching incorporated, could you run very simple like C programs and say do it in parallel and have some mass kind of calculation?
Yes. That's kind of what I spend my career doing. So, yes, we'll have a couple lectures on what general purpose computability and sort of what it can do and what it can't. It's fair to think of these processors as very simple processors compared to what you see on a CPU. Okay, they don't have any crazy out of order stuff or branch prediction or none of that stuff. It's a very simple pipeline. On the other hand, there's lots of them. There's hundreds of them. So. I'll have a slide where I talk about a Seymour Cray quote that's, would you rather plow a field with 2 strong oxen or 1,024 chickens? All right? So CPU approach is the oxen approach. Okay? This is the chicken approach, that we have hundreds of little tiny processors. Can we put them together to do something big? Okay. So one thing you can look at in terms of this instruction set is this instruction set is very specific to doing vertex processing. Okay? When they were making up this instruction set, they said, okay, we're processing vertices. We're going to need to do lighting kind of operations on vertices. So we're going to have this lit instruction. You know, reciprocal square root, right? That's only for dealing with normals. We deal with normals a lot in vertices, you know, dot products and stuff. This is very specific. And so when you look at how this thing was derived, right, this was an instruction set for vertices. And we're going to have a different instruction set for fragments. Okay? And we started out doing that. We had a very different instruction set for the two. As time goes on, instruction sets broaden. These instruction sets start getting closer together. And so we're moving from a period of having 2 totally different instruction sets to having the same instruction set. We're also moving from having 2 different, task parallel models to having a more time multiplexed model. And those 2 things are sort of happening in concert, and they're both the same direction as far as the trend goes. So when we look at this picture here, we're seeing a vertex processor and a fragment processor differently. What happens when we have just one pool of processors? Well, that better run all the instructions for all of them, and that's sort of where we've arrived now. The latest standards have the same instruction set for vertices and fragments. Okay, so now I'm going to talk about fragments for the next 15 minutes. Okay, so here's what fragments do. We're saying, well, sort of texture and fragment operations, what's going on there? Lots of stuff is going on here. What we're really concerned about is we're going to go out and get a bunch of texture stuff, and we're going to calculate colors and end up with one color at the end. Okay? That's our goal. We might go to texture and get a bunch of things, but we're going to end up having basically a shade tree kind of approach, and at the bottom, we're going to have come out one color. Okay? And we're going to want an instruction set that looks like that. So the big difference between the fragment program, at least the original fragment program, and the original vertex program is the fragment processor needed to go out and talk to texture. Other than that, they look very similar. So we look at this picture here. It looks pretty much the same. Okay? Doesn't have constant registers, does have textures. Okay? Here's Microsoft's really groovy picture. Right? What does that look like? Pretty much the same thing, although they're completely missing the textures. Good job, guys. Okay. What we do have here is the color, the output color. We also have to somehow compute the output depth, how far away that is. Okay? Basically, this is the same picture, though. All right? So what are the inputs here? Okay? Inputs are maybe a couple colors and a bunch of texture coordinates. Okay? That's what we're going to use to put things together. All right? Outputs, color and depth. Right? This is a little bit more restricted as far as what we have to do. Instructions. Okay? So this has a totally different instruction set. At least it started out being totally different. Okay? We got to subtract, for instance. Okay? We have a LERP instruction. Okay? LERP stands for linear interpolation. All right? We have one color here. We have one color here. We have some value from 0 to 1, and it's going to blend between those based on the linear interpolate. Right? So we have red and blue. If the interpolation parameter is 0.5, then we're going to have purple. If it's 0.99, we're going to have blue. If it's 0.01, we're going to have red. Right? So it's sort of like this scale. Okay? You do that a lot in a fragment processor. Great. It has dot products. It has a comparison operator and a conditional. Okay? But look what they do. They're not like actual branches or anything. It's got some texture stuff the other guy doesn't have. Okay? Different instruction set. All right? So what does that actually look like in hardware? Okay? So now we're looking at the fragment processors here. Okay? Again, this is a marketing slide, so I'm not even going to explain any of this. One thing is that it is a SIMD architecture. What they found was textures don't need to branch very much. Fragments don't need to branch very much, so we can build a SIMD architecture there. Okay, they've got a couple different math units here. This is sort of the buffed math unit. This guy does less functions than that math unit does, but they're nice and pipelined. And at least the newer ones, when we get to future texture shader standards, these start to branch more. Okay, they also have to be able to talk to texture. So as time goes on, okay, we start having more and more features there. We can talk to more and more textures. We can interpolate more and more colors. We can have more textures bound. Instead of just having one texture available to us at a time, we can now have more. We can have dependent textures. Okay? And what I mean there is that you look up a texture value, you bring back the value, you do some computation with the value, and you use that as an address and go out again. Okay? So that's like a doubly indexed kind of operation there. Okay? Eventually, we get to the point where we can do that in arbitrary amount, but early hardware didn't really do that. Pixel Shader 3 added actual conditionals. It was still SIMD processing, but it would sort of take care of all the masking for you. Okay? You could add swizzles. You could have sine and cosine. There's some gradient stuff. It did some other groovy kinds of things. Okay? So this is what the fragment hardware looked like. As time goes on, the Vertex shader instruction set and the fragment shader gets closer together. They add features. Okay, these original ones work on. The original ones, I believe, worked on. No, these were floating point. Okay, so they're floating point all the way through. We've recently added integers also, though. Okay, originally all these standards only worked on floating point numbers. Okay, this is also a 4-wide vector. Okay, so something else that they noticed is that as time goes on, some part of your processing is 4-wide, and some part of your processing is 1-wide. As time goes on, the proportion that's 1-wide gets bigger and bigger. And the proportion that's 4-wide gets smaller and smaller. And Pixar noticed this too. When Pixar does RenderMan stuff, if you do really complicated RenderMan shaders, there's not a lot of vectorized code. Most of it's scalar. So today, NVIDIA has decided we're not going to build 4-wide hardware anymore. We're only going to build 1-wide hardware. Okay? And that's what they've done in their latest chips. ATI has not done that yet. ATI actually has 5-wide hardware, so they can do a 4-wide operation and a 1-wide operation at the same time. But they feel that it still makes sense to have 4-wide hardware. Okay? That's sort of a difference between the two companies. Okay, so what do we actually do with these? Right? So we've seen all these standards and stuff. What does a real program actually look like? Okay, so maybe 2 years ago or something, one of the students, or two of the students, did a project where they took Doom 3 and they used tracing utilities to pull the programs out of that. Okay, so what do they actually do? And so they sucked out all the fragment shaders from Doom 3, and then they did an analysis of sort of what was going on. Okay, so they used a different lighting model. Okay, they used a different lighting model than what OpenGL did. That was kind of cool. They used different ways to combine fragments. So I sort of have all these equations up here. The other thing they did is they used a lot more textures. Okay, so if we look over here, these are all the textures that are used in the fragment shader. Okay, so this is what's called a bump texture, and what you're looking at there is basically to take instead of using lots and lots of triangles to model a bumpy surface, what they do instead is they take a nice flat sheet and then they move the normals a little bit, and it's not bumpy, but it looks like it's bumpy. And the question is, what do those normals actually look like? Okay? And so you have a whole texture map that stores normals. Not colors, stores normals. And you look up those normals. We're not talking about bump mapping as a there are classes that will teach you about how to use bump mapping. I'm just giving a high-level thing. Okay? This is a texture that has the diffuse color. This one is really hard to see, but if you look at the top, you can see a little bit. This is the specular texture. So you're looking up the colors that are there. Okay? This is really interesting. Normalization cube test. Normalization cube texture. So at some point in here, they have to normalize a vector in the fragment shader. So you could do that by actually calculating it, or you can take the normal and look it up in a texture map and get back how long it is. Okay? Which seems really weird, but the Doom guys figured that was faster. Rather than calculate the reciprocal square root and do all the math you need to do to figure out how long it is, just look it up in a texture. Okay? Then to calculate light fall off. So I think that's like directional. How do we calculate that? We have another texture to be able to do that. And then calculate the light projection. Again, rather than compute that, they had a texture to be able to do that. So they felt that looking things up in this particular architecture was better than actually computing them. That will not be true in the long run, but these guys kind of know what they're doing, and that's what they chose to do in their shader. So it was a really interesting analysis. One of my grad students, Eric Lingel, he sent this one here. So this is a floor. It's a pretty good-looking floor. And it uses a bunch of techniques to be able to do it, to be able to make it look good. In particular, what he's interested in is getting shadows right. Okay, so if you look here, you can tell that's a bumpy floor because the shadows look really good. Like if you look in the grout, you could see some shadow kinds of terms. And it turns out you can take care of that in your shader. And let's see. Right, so he uses 4 different, this is a bump map here. Okay, so this is sort of what the color is. This is which way the normals are pointing, because you do lighting based on that. And this is what's called a horizon map. And if you're in the grout, it sort of tells you what fraction of the sky you can see. Okay, so if you're down in the grout, you can't see very much sky, so you shouldn't get a lot of light. If you're on the surface of one of these tiles, you should get more light. And that's sort of what this is telling you. And he's got a horizon map for the XY direction, for the X direction, and for the Y direction. So you clearly can't read all this. But it's about 60 instructions. And it just sort of shows how things are put together. All right, so this is written actually in assembly language. If you look up at the very top, it says ARB FTP 1.0. That's the OpenGL Architecture Review Board Floating Point Standard 1.0. And it uses NV Fragment Program 2. So this is version 2 of the Fragment Program Standard. Okay? And so this is sort of showing how do you put this thing together to end up getting a sophisticated looking effect using the bump mapping and the horizon mapping and the parallax mapping. Right? So this is this would be in the range of what games would use today in terms of the complexity of what's actually going on. Cool? All right, so where are we going? All right, so this is the DirectX 10 pipeline. If you're buying a graphics card today, then this is often what you're going to get. So they did something new. All right, so we know about the vertex shaders. We know about the fragment or pixel shaders. Microsoft calls them pixel shaders. Everybody else calls them fragment shaders. DirectX 10 has a third stage, and that's the geometry shader. Okay, basically what this does is this guy works on vertices. This guy works on fragments. This guy works on triangles. Okay? You have a whole triangle. You have 3 vertices that make a triangle. What do you do with it? And so one thing, the big thing that they did with this stage is that this is one in, one out, period. Right? Always one in, always one out. Makes it very easy to parallelize. Okay? This guy is one in, either 0 or 1 out. Okay? The fragment program actually lets you kill a fragment. Makes it a little bit harder to parallelize, but again, only 1 in, either 1 or 0 out. Okay? This guy is 1 in and anywhere from 0 to 4 out. So what it's really good at, why they designed it, was to do tessellation. You send in a triangle like this, you get out a triangle like this. Okay? You get out 4 triangles. Then you can wrap it around and say, okay, I'm going to send in this triangle, and we're going to send out 4 triangles here. And you can take a big triangle and tessellate it into smaller triangles. Okay, that's a very desirable thing to do in particular circumstances. Okay, so they're still learning to get this right. I would say modern geometry shaders, not the most performance optimal thing. Okay, it's hard to use a geometry shader and get good performance out of it because they're having a real hard time parallelizing that because you can have anywhere from 0 to 4 out.
I'm a bit confused as to, so you say it's the DirectX 10 pipeline, but you said also the hardware of the pipeline in the NVIDIA card or the ATI card, it's fixed because it's hardware.
Yes.
So is this they're imposing on the ATI and AMD, put in this geometry shader for us?
Yes. So it's fair to say that Microsoft is driving a lot of the graphics standards from a software point of view. And they fly up all these guys from NVIDIA and Intel and AMD, and they put them all in a room, and they say, here's the things we'd like to do. And then these guys say, well, here's the things we'd like to do, and we don't want to do your things because of X. And then they spend years working this out. And so, I mean, it's good because Microsoft's driving new standards, and they're putting really cool new things in there. And they make sure that they put things in there that the graphics hardware people feel that they can actually build. So I think it's been successful from that point of view. It is known that having like this sort of capability would be very useful in the pipeline. It's just hard to parallelize it and make it right.
So, I mean, the geometry shader seems like a really bad thing to do on like the unified architecture thing, since it has to split every, it's hard to parallelize. So doesn't it make sense to again move back to the space domain and somehow,
right.
time, space, and loop it back into each other somehow?
So one of the enormous questions in graphics architecture is you've got this big complicated graphics pipeline. What do you build in special purpose hardware, and what do you put in the programmable pipeline? Okay? There's not a correct answer to this problem. Right? We are going to have people from NVIDIA and AMD up here, and they will argue, compared to Intel, that they feel more things should be fixed function. Okay? They will feel in particular that the rasterizer, for instance, should be a fixed function unit. And Intel's going to come in here, and they're going to tell you that this whole thing should be done in software. Okay? Intel, the Larrabee architecture they're proposing, does almost the entire pipeline in software. They have some texture hardware that's hardware, special purpose hardware, but most of the rest of it is software. Okay? There's not a right answer, or we don't know what the right answer is yet. There are people taking different approaches. So does it make sense to take this, rip it out of the programmable shader, turn into something fixed function? Sure, but then you lose the programmability aspects of it. Okay? You can't programmably figure this out, like how you're going to do your tessellation.
Well, maybe you could have it like a different architecture and still be programmable, just in a different way. Like rip it out of the unified architecture and have some kind of other way, like a MIMD way to program it, and then somehow feed all that information back into the unified.
And the right thing to do when NVIDIA and ATI show up is to say, why do your geometry shaders suck? Okay, because that's really what we want to know. It's like, well, they're not very good. It's hard to get good performance through them. It turns out it's better to do things through the general purpose interface, and I can take that offline with you. But if we look at something like marching cubes, which is a visualization particular task to do, that some visualization people in here probably know. Okay, it turns out it's better to do that in the general purpose interface than use the geometry shaders because the geometry shaders are so bad. Okay? But you're often going to see the hardware architects, they're going to put something in. It's not going to have good performance. They're going to figure out how people are going to use it. And then the next time they build it, they're going to do it right. You'll see that a lot. Okay, that was like it for the original Vertex and fragment shaders. They weren't great. But over time, they got better because they learned how people were actually going to use it. Okay, just checking if there's anything. Okay, probably the last thing here that I want to say is this move from, and this sort of sets the stage for some of the computing things that we'll be talking about. It used to be this is the way you talk to the graphics processor, right? You would use a high-level graphics language which would go through an OpenGL driver or a Direct3D driver, which would then again talk to some low-level graphics driver. You got to talk to this. you didn't get to talk to those guys. And so people wanted to have direct access to the compute units. Okay, they wanted to say, you've got all these great compute units on here. We don't want to have to go through OpenGL to get to them. We want to talk to them directly. And the real exciting thing that's happening is people are building compute drivers and low-level APIs to talk to the hardware directly, and building high-level languages just for compute to use this hardware that we built for things that are not just graphics shaders. Okay? And I believe that's on the schedule for what we're going to talk about next week. Have a good weekend. Oh, at least one person asked me to borrow a graphics card. So if you want to borrow a graphics card because yours is insufficient for whatever, come talk to me.